This week, we're showcasing a new bi-monthly programme strand from The Naked Scientists, which we're making in collaboration with the folks at Diamond, the UK's synchrotron light source. The programme's published on our website at thenakedscientists.com/diamond and as the Diamond Light Source podcast in iTunes. Here's the latest episode.
From Diamond Light Source, this is the Diamond Podcast.
Welcome to the Diamond Light Source podcast. In this edition, we look into the field of cultural heritage to see how scientists at Diamond are discovering new ways to keep our history preserved. We'll be finding out how synchrotron light can be used to develop new ways to conserve historical treasures, such as the Mary Rose.
What we tend to look at is either where elements are in a material or the structure of the material itself. So it will either have something to do with conservation and the way things are surviving or the way they're being preserved, something like the Mary Rose, where they're trying to understand how their conservation treatment is really working.
Jen Hiller will be discussing the role of cultural heritage at Diamond. Plus, we learn how scientists are trying to solve a mystery in the art world.
It certainly occurs in paintings. It's an effect where you get, a large area of red paint produced with vermilion, but it can go from a sort of grey to black colour, and it can be quite patchy, but it's very sort of disfiguring to the appearance of the painting.
Nicholas Easter will be explaining how his team are looking into this phenomenon to prevent it ruining major works of art. All that, plus the latest news from the events and festivals that took place over the summer. I'm Mira Senthilingam, and this is the Diamond Podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
Now, before we take a look at how Diamond is delving deep into the world of cultural heritage, let's join Sarah Bucknell from Diamond's communications team to find out what Diamond's been up to over the summer.
We've had a really busy summer, actually. At the end of June and early July, we were at the World Conference of Science Journalists and the Royal Society Summer Science Exhibition, now both in London. It was the first time the World Conference of Science Journalists came to the UK, and Diamond sponsored the official welcome reception through lightsources.org. And we also did a news briefing at the French Institute in South Kensington, and that was with the French Synchrotron Soleil and Elettra in Italy. One of our users, Dr. Mark Sanderson from King's College London, spoke about the recently published results of his research into antibacterial drugs that are used to treat the bacteria responsible for things like pneumonia and meningitis, and how the bacteria can sometimes develop a resistance to these drugs.
You also organised a few trips at the conference, didn't you?
Yeah, we put on a post-conference trip as part of the week's events. So a number of the science journalist delegates came to Oxfordshire to visit 4 of its large research facilities. So that was the Joint European Torus, or JET, at Culham, the Central Laser Facility and ISIS at the Rutherford Appleton Laboratory, and of course Diamond.
So it sounds like you had a lot of really interesting events taking place at the World Conference of Science Journalists, but as you mentioned also that week, you were at the Royal Society's summer exhibition.
That's right, we were involved on 2 of their stands. We had textile panels from our Designs for Life Science and Art project on display. This was a project which was carried out a couple of years ago in collaboration with the Oxford Trust and the Oxfordshire Federation of Women's Institutes, the WI. The WI ladies met with a number of Diamond scientists to debate science research priorities, and as a result they produced 30 panels of textile art which depict the viruses and diseases that are studied at Diamond. So we had those on display at the exhibition.
So obviously the communications team have been very busy out and about, but what was happening actually back here at the fort at Diamond? So how are the new beamlines getting along?
The Phase 2 beamlines are coming on really well. At the end of June, the first turf was cut to make way for I-13, and that's an imaging and coherence beamline. And when complete, it will stretch 250 metres away from the main synchrotron building, and it will be used for coherence and tomography experiments. For example, researchers will be able to create 3D images of objects in extremely minute detail. The first users are expected on this beamline in 2011.
You've also got another Inside Diamond Day coming up.
Yep, our next Inside Diamond Day is on Saturday, 3rd of October. People are welcome to register and they can do so on our website.
Thanks, Sarah. That was Diamond's Sarah Bucknell. We'll be back with more of the latest news and events from Diamond in the next podcast. Now, this month, we're digging deep into the world of archaeology to learn how scientists are helping preserve our historical treasures. So first, we meet Diamond's resident archaeologist, Jen Hiller, down by the synchrotron, to find out just what cultural heritage science involves.
Well, cultural heritage at Diamond tends to focus on materials characterization or materials degradation. So the beamlines that are involved in it now are primarily the non-crystalline diffraction beamline and the X-ray fluorescence or XAFS beamline. But there will be at least 3 more that are involved in cultural heritage projects over time as they come online. And what we tend to look at is either where elements are in a material or the structure of the material itself. So it will either have something to do with conservation and the way things are surviving or the way they're being preserved, something like the Mary Rose, where they're trying to understand how their conservation treatment is really working, or something like what we look at here, which is how collagen-based materials like parchment, leather, and bone degrade over time and what kind of ways we either can conserve them or gather all the information that we can from them as they degrade.
So first of all, you've mentioned that it's possible to look at elements within various samples that need to be looked at. So how is that possible here, and why does that help learn more about cultural heritage?
It's a technique called XAFS that localizes elements by using a tunable energy or tunable wavelength coming out of the monochromator, which is something you can really only do at a synchrotron source. Laboratory-based sources are fixed wavelength. So by changing the wavelength, they excite different molecules at different times, and each element will fluoresce in a different way, which gives you an idea of where elements are localized. And the wonderful thing that we have here is a beamline that runs that technique with a micron scale resolution, so about 100 times smaller than a human hair, which makes it easy to look at very localized areas within a structure to try to understand how far things are spreading, or to look at very tiny things like how far ink penetrates into paper, how a single bit of pigment on the surface of a painting can be affected by its environment and by the conservation treatments applied to it.
So that's work done at the microfocus spectroscopy beamline, but the particular beamline we're sitting at now is the non-crystalline diffraction beamline. So what takes place here? Is this where you look at structure of materials?
We do look at structure of materials, and we look at structure of all kinds of materials, but preferably things that either won't grow into a crystal because they're already partially ordered, or you don't want to have grow into a crystal because you'd rather look at them in their native state. So this beamline actually covers probably about 60% physical science and about 40% life science. But a lot of what we do in life science is look at collagen-based materials, and there are archaeological and cultural heritage objects that are basically collagen-based materials. And the best example that we have, and certainly the most publicized example that's been looked at here, are parchments. Parchment is most of European written heritage, but it's type 1 collagen, it's animal skin. So it's really the same as the type 1 collagen anywhere in the human body, and type 1 collagen is present everywhere. In bone, in cornea, in skin, it's holding all of your bits together, really. So when that material, for all we understand of the structure of that material and all the biologists that we have that study that kind of material to understand how to heal it, to how to repair it, they can also look at these documents, these very precious documents. In some cases, we've had fragments of the Dead Sea Scrolls. Groups have looked at the Magna Carta to try to understand how that collagen structure is degrading. And the problem with collagen is as it degrades, it turns into gelatin. And gelatin is really the same thing that happens when you boil a soup bone for too long, and it goes to that horrible jelly sort of sludge. That actually happens to parchment as it changes over time. And if the native collagen structure is lost, then conservation treatments can destroy the parchment very quickly, especially if you get it wet. So they're very susceptible to floods, they're very susceptible to humidity, cleaning, you name it. So a lot of people are trying to understand how best to preserve parchments for as long as possible, because it's so much of written heritage, but also to understand how their manufacture, the very ink that was used to write on them, all of those factors can also affect their preservation. So the non-crystalline diffraction beamline right now mainly impacts cultural heritage in that area. And the really nice thing about bringing something like parchment here is that it's very fast to take the measurements. The technique is non-destructive, and we're quite gentle. The X-rays are actually, believe it or not, quite gentle to historic parchment, so you can take it back out. We also have the advantage of very, very high spatial resolution, so we can look at tiny, tiny fragments of things. So people do bring things here that have been micro-sampled, cut little tiny slivers out, things that would be almost impossible to analyze with any other source because you need a very, very small beam.
So just how small do these samples get then?
They can be sometimes only a few millimeters across. And for something that's, if it's as small as 1 millimeter across, then that's actually, we can look at that in cross-section. So we can look at the way the surfaces are differently affected than the middle of the parchment too. 1 millimeter actually allows us to view it from both sides.
So these two beamlines are the main ones involved with cultural heritage at the moment, but what other ones have you got coming up, and as a result of those, what potential new avenues will there be for cultural heritage research?
There are at least 3. There's the infrared beamline, which is coming online quite soon, and they can look at things like pigmentation. There's an idea to look at lipid residues in pots. There's the powder diffraction beamline, which is actually online now. I don't know if they're doing any cultural heritage work at present, but that looks at more of traditional X-ray diffraction, so it can look at composition of materials. And then there's the tomography beamline, which could look at, repairs to larger artifacts, things like almost entire museum bronzes. So there's at least those 3. And it's down to the creativity of the users whether the other ones get exploited as well for cultural heritage.
Diamond's resident archaeologist Jen Hiller explaining how X-rays can be used to probe minute samples of historical gems such as the Dead Sea Scrolls to investigate their structure and develop new methods of preservation.
Did you know that diamond is made of more than 2,000 tonnes of steel? That's the same as 300 London buses.
You're listening to the Diamond Light Source podcast, and in this edition, we're looking at the role of science in cultural heritage. Now, we've had an outline of the role synchrotron light can play in maintaining our cultural heritage. So now we meet the scientists behind the samples to see what they've discovered so far. Coming up, we'll be learning how masterpieces such as Turner's paintings are randomly changing, and what scientists are doing to try and find out more about this and stop it. But first, we go out to sea to hear the story of the Mary Rose and how Mark Jones from the Mary Rose Trust is going about keeping this iconic ship in its best condition.
The Tudor warship Mary Rose was built between 1509 and 1511 in Portsmouth, and she sailed successfully for almost 35 years. And she was the very first purpose-built warship in the Royal Fleet. And on a fateful day in 1545, she was about to engage the French invasion fleet. She sunk in about 14 metres of water, and there she lay undisturbed for almost 437 years. She was recovered in 1982.
Once the ship was recovered, what was initially done to preserve it?
The first thing we did, of course, was to spray it with seawater. She was then taken into a dry dock, and over the dry dock we built a ship hull. Within this ship hull, we created an environment in which the ship timbers were sprayed constantly with chilled fresh water to reduce the activity of microbes such as bacteria and fungi. In addition to that, we cleaned the surface, and also we started to wash out iron compounds that had actually penetrated into the wood structure. And these iron compounds came from corroding cast and wrought iron guns, and also iron fittings such as nails and bolts, which held the ship together.
And so now you're actually probing down and looking into the actual cells of the wood and the timber to try and find new ways to preserve it even more.
Since 1994, she's undergone a process of preservation involving a water-soluble wax called polyethylene glycol. But apart from that, we're very interested in the detailed chemistry within the wood itself. We've used all sorts of techniques to analyse the condition of the wood, Fourier transform, infrared spectroscopy, to look at the changes to the chemistry of the cell material in terms of cellulose, hemicellulose and lignin. In addition to that, we're actually finding a number of compounds present in the wood, such as iron and sulfur compounds.
So how are you now looking down into the wood cells to look at the interactions of the iron and the sulfur in these cells? We've
been very lucky, really, to work very closely with government scientists to look at the current preservation treatment of the Mary Rose from 2 points of view. First of all, stabilisation, but also to prevent these iron and sulfur compounds forming acids in the timber in the future. To achieve this, we've got to have a detailed understanding of the chemistry of both these compounds and the interactions between the two. And what we're trying to prevent is the production of sulfuric acid in the timber due to the oxidation of iron sulfur compounds such as iron sulfide, which over time will form sulfuric acid.
And so which beamline at the synchrotron are you using, and how is this helping you to visualise the cells and the interactions of the iron and the sulphur?
Well, we're using station I-18, and we have been able to use X-rays to probe the atomic structure of these compounds and the interaction between the two compounds, such as iron and sulphur. So we've identified the different types of sulphur compounds. We've also used this station to identify the location of these iron and sulphur compounds. We've also identified deep in the ship timber organosulfur compounds such as cysteine, cystine and thiols. And these are linked into part of the cell wall which we call the mid lamella, which is very rich in lignin.
So having now identified all of these different compounds, what can you do with this information to then help preserve the ship a lot better?
We are developing ongoing treatments to supplement polyethylene glycol treatment, which the ship is undergoing at the moment, to stabilise these iron and sulphur compounds in the wood. We're trying to wash out as much as we can. Anything that we don't get out, we're trying to make them inactive.
And so what are the actual treatments you've come up with?
One is called calcium phytate, which has proved very successful in the removal of iron sulphur compounds from archaeological wood. In addition to that, it also acts as an antioxidant, which prevents further reactions to any of the sulphur iron compounds that still remain in the timbers. We think we'll introduce this particular chemical to the spray system, and this will form part of the final treatment for the ship timber. So we'll have stabilised it using polyethylene glycol, remove substantial amounts of iron compounds using calcium phytate, but also putting more calcium phytate in to prevent anything that still remains inside the wood from developing into sulfuric acid.
So the main real problem is the creation of sulfuric acid, so this is really what you want to prevent?
Yeah, which can then destroy the cellular structure of the wood cell wall.
Coming up with these various treatments to absorb the iron, is there any risk of these having adverse effects on the timber?
Well, that's a very good question. One of the problems, of course, when you add a new chemical to the wood is what's going to happen long term to this chemical. Apart from finding out a suitable treatment, is to look at their long term effects on the well-being of the ship itself. So, in addition to finding new treatments, we're actually trying to find out what happens to these new treatments over time, whether these can be converted either by bacteria or by oxidation reduction sort of mechanisms in the wood into harmful chemicals. So we've got to make sure that they don't.
So how are you going about doing that? Are you just putting samples of it on small bits?
We take test samples, and we do lots of laboratory experiments, and then we take these samples to Diamond. And using these facilities, we've been able to look at the different chemistries at the cellular level, which has been fantastic, which you cannot do in any university laboratory.
Mark Jones from the Mary Rose Trust, explaining how an understanding of the wood in the Mary Rose and its components can help target better treatments for its preservation. Now, it's not only the nautical world that's being probed by cultural heritage science, but also the art world. For many years, a mystery has perplexed artists and art historians the world over, as certain masterpieces have begun changing in appearance. And the pieces involved are where the red pigment vermilion has been used. This pigment is extracted from the mineral cinnabar. And to find out more about the use of this colour and just why these changes could be happening, I met Nicholas Eastar from the Pigmentum Project.
Cinnabar is essentially mercury sulfide. The synthetic version that's known as vermilion, rather than use a mineral which can be impure, if you take the mercury out of the cinnabar, you can then recombine it with sulphur to form vermilion synthetically. And you get this pure, bright red material, which is very nice to paint with. In essence, you've got three materials that might be used by artists. There's the cinnabar mineral itself, and then two forms of a synthetic product. They're all mercury sulfide, they're all red, but they have slightly different properties.
What forms of historical art then have used this vermilion?
Artists use these pigments for all sorts of painting purposes, and you can find it in everything from an easel painting in the National Gallery through a piece of sculpture like the Chinese terracotta warriors to a wall painting that you might find in Pompeii.
So you have some samples of cinnabar here.
Yes, I've got two different samples of the cinnabar mineral here, both from quite famous historical sources. One in particular, a Spanish cinnabar from Almaden, and another one that's actually from Italy, a place called Monte Amiata. And we know that these were both used historically by artists as sources.
Now, looking at one, they look very different because one has essentially got a kind of darkened coating around it, whilst the other appears to have more ash with it.
Yes, I mean, it's partly to do with the geological context of these, but also probably with this sample from Spain, you've got some discolouring of the mercury sulfide itself, which is essentially the research that we're trying to do. Just what is this darkened material and how does it occur? It certainly occurs in paintings. It's an effect where you get, a large area of red paint produced with vermilion, but it can go from a sort of grey to black colour, and it can be quite patchy, but it's very sort of disfiguring to the appearance of the painting.
And does this happen in most paintings that the vermilion has been used on?
No, it only happens in certain circumstances, and it's the circumstances that we're interested in. Just why does it happen sometimes, not always?
And so how have you gone about looking into this?
We can approach these kinds of problems in various ways. One can look at the paintings that it's happened in and what kind of context they come from. Is it paintings from a certain place and time? Is there an effect perhaps from the atmosphere, both where the paintings were produced or perhaps where they've been subsequently displayed? But we're interested in the chemistry of it.
What's thought so far as to why it does change from red to black?
In fact, there are a number of theories that have been put forward. In certain circumstances, you could take a bright red piece of cinnabar out of the ground and bring it into the light, and it would really quite rapidly change to black. And people were suggesting things like it might be that small amounts of mercury were forming on the surface, and that in thin layers can appear black. Other theories have been to do with the fact that there's a very closely related mineral structure, metacinnabar. So not cinnabar, but metacinnabar. And metacinnabar happens to be black. So is it, in this case, that there is a conversion going on in the crystal structure between the red cinnabar and the black metacinnabar? Then again, another possibility is that these are quite interesting compounds chemically anyway, that they're related to a group of compounds that are semiconductors that happen to be responsive to light in the infrared. It's possible to modify the semiconductor properties of mercury sulfide so that it shifts from being a red colour to a black colour.
So that's quite a few theories then as to why it could be happening. What have you been looking into so far with the use of synchrotron light to try and figure out which of these theories it is?
Synchrotron radiation allows us to apply a number of different sorts of investigation. Probably a key thing is that we can look at very, very small samples because you have an intense beam of radiation. If we do take samples from objects, we don't need very much, and obviously that for a valuable object that's highly desirable.
Yes, I can hardly imagine the owners of these paintings wanting large chunks taken out.
They're quite reluctant, to say the least. But also there are techniques that we can use to look at the chemical structure inside. You can even follow the process of alteration. So if you've got a reaction taking place, you can monitor it using synchrotron techniques. But we're interested really in changes to the crystal structure. Is there a slight change in position of sulfur with respect to mercury? And then again, we're interested in very small amounts of trace elements that may be present that can act as factors that sort of induce this conversion, particularly things like the presence of chlorine has been suggested in the past as a mechanism that can promote this blackening.
Which beamline do you use at Diamond for this, and how does this actually help you see the position and location of these elements?
We've been using beamline I-18, microfocus X-ray source, that allows us to do this detailed elemental mapping of samples so we can get down to very high resolution, spatial resolution. But we can also run these techniques that allow us to look at the actual crystallography of the cinnabar.
And I guess so the big question is, what have you managed to find so far?
That's the $64,000 question. Out of the various possibilities, one of the areas that we've been looking into especially closely is this presence of chlorine. That's been found as a potential mechanism in wall paintings in Pompeii. But we're looking quite seriously now at these semiconductor properties. Is a kind of obvious mechanism if one starts to look at those sorts of chemical structures, that it's possible to get these kinds of shifts from red to black. But we need to do further work at this stage to pursue that. We won't necessarily find that in all circumstances it's the same mechanism at play. The sheer fact that there are a number of proposed mechanisms for this strongly suggests that in different circumstances different mechanisms may be operating.
Nicholas Eastahl from the Pigmentum Project, discussing the possible reasons why paintings such as those by Turner are turning in colour. And like many pieces of art, it's a work in progress. Now, that's it for this edition of the Diamond Podcast, but make sure you join us again in November, when we'll be back with more of the latest news and discoveries from Diamond, as well as a look into the earth sciences, ranging from earthquakes to meteorites, to discover just what synchrotrons can tell us about the universe on the planetary scale. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk. Thank you to Sarah Bucknell, Jen Hiller, Mark Jones and Nicholas Eastahl. I'm Mira Senthilingam. Thank you for listening and see you next time.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.
If you'd like to subscribe to the Diamond Podcast for more insights into the research that's taking place at Diamond, details are on our website at thenakedscientists.com/diamond, or you can subscribe via iTunes. Thanks for listening.